Okay, so in this video, we're going to focus on matrices and linear transformations. All right, now there are two kind of theorems that are kind of paired with each other. They work kind of together, right? Now the first one is theorem MBLT. So this states that for any m by n matrix, defined for any m by n matrix, you can define T of x equals to ax. All right, then T from C, or say Rn to Rm is a linear combination. All right. So really here, the fact any matrix now, if you multiply by some vector x, represents some kind of linear transformation. All right. And this just follows from properties of matrix multiplication and matrix addition. So for instance here, if let's say we had T of x plus y. Right. This is going to be a x plus y, and I can distribute here along the left to get ax plus ay, and we could see, well, these are just here the way we define the linear transformation of x plus the linear transformation, the t of y. Okay, and the same goes for the scalar multiplication. If you have this, then you can define this here, and the associative, you can actually write this as a x, right? Well, this is just t of x. So we could see that it preserves that scalar multiplication and the addition across the transformation here. Okay, so on the converse, so the other theorem states, so now we know what this theorem states, that if I have any matrix A, then it represents a linear combination, right? So secretly, all those matrices that we've been working with, those are actually representing linear transformations. All right, now the second theorem, MLTCV. This is the matrix of a linear transformation. What this theorem says, this is the converse, where it says every linear transformation, I'll just shorthand LT, defined across Rn to CRM, is given by Tx equals to Ax by some matrix multiplication, right, for some matrix A, right? Now we can construct the columns of A simply by taking the outputs of the standard unit vectors, right? So one way that you can construct A is by taking the outputs of E1, right? That'll be your first column. E2, that'll be your second column, etc., until you get to En, right? And that'll be your nth column. Okay. All right. So here, let's say, another way you can do this here, well, here, let's take a look at our previous from our previous video, we defined the linear transformation T of x1, x2 to be x1 plus x2, x1 minus x2 over 2 x1. So what the above theorem states is that I can generate this matrix by calculating T of E1 and T of E2. All right. Now again, T of E1 is T of 1, 0. So that gives me 1, 1, 2. Okay. And now T of E2 would be T of 0, 1. And this would give me 1, negative 1, 0. Okay, so now I can represent T of x1, x2. Instead of doing this, I can represent it as 1, 1, 2, 1, negative 1, 0 times the vector x1, x2. So now I've written it, I'm able to write it as matrix multiplication. And I can do this for any linear transformation across our Euclidean n space. Okay? All right. Now, this kind of leads us to our last theorem here to wrap up this section here, where let's say that so here's kind of the culmination of what we've been talking about here. This is theorem LT dB. So this is a linear transformation defined on a basis. So let's say that B is U sub n. Right? It's a basis for U. And V1 through Vn are any vectors in V. Then there is a unique linear transformation T from U1 to V such that T of U sub I is equal, sorry, let me stay consistent with my vector notation here, V sub I for each I. All right, now what this is stating here is that any linear transformation we can define any linear transformation we want simply by declaring where the basis vectors go. The rest of the transformation is forced by the linearity of that linear transformation. Okay, so here, think of it like this, right? So let's say that W is an element of the vector space U. Now I know the set B is a basis, so W must be written, must be able to be defined as a linear combination of those vectors. It has to be, right? It's a basis, right? The defining characteristic of a basis, well, one of the defining characteristics is that you can write any vector space, any vector from the designated vector space that it is a basis of as a linear combination of those vectors. Right? The second property is that it's linear independent. Right? But anyways, the important part here is that W, since it lives in U, must be able to be written as a linear combination of those basis vectors. All right, and then T of W, right? Of course, since the linear combinations are preserved, must be written as A1 V1 plus dot 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 A sub n V sub n. All right, and you could say, kind of taking your turns here, letting each one of those go to 0, right? A1 and V1, let's say A1 is non-zero, and let the rest go to 0, and you can see why the above must be true here. Okay, and again, right, what this theorem is telling me is that all I need to know is what a transformation does, or I just need to define what a transformation does to the basis vectors, and everything else I can just generate from the linearity of the linear transformation. So let's do an example here. So I want to create a linear transformation between the polynomial space P3 and 2 by 2 matrices. All right, so first I need a basis for P3, and I'll choose the standard basis of 1x squared x cubed. All right, and I'll define what the transformation does to each one of these vectors. Okay, so what I'll do is I'll say, let's say that T of 1 maps onto 1, 0, 0, 1. Right, T of x, or 1x, I should say here, will map onto, 0. Will map onto 0, 1, 0, 0. T of 1 times x squared will map onto here, 0, 0, 1, 0. Right, and then lastly, the transformation of 1 times x cubed maps onto 0, 0, 1. All right, now this represents a linear transformation, right, which you can verify. All right, but more importantly, I know what this transformation does to the basis vectors of my domain. All right, so that means now I can generate the linear transformation of any vector inside of my domain. Right, so what I can do is I can take the linear transformation of this polynomial, right? I don't need to know anything else about the transformation other than what it does to the basis vectors. Because now, through the properties of linear transformation, I can write this as 2 times T of 1 plus 3 times T of 1 times x, right, minus 4 T of x squared, and then plus T of x cubed. All right, and we could see this gives me 2, 0, 0, 0, plus 0, 3, 0, 0, plus 0, 0, minus 4, 0. And then the last one is just the standard 0, 0, 1. And then this adding gives me the following matrix. Okay, and in general, right, we could see the pattern here. The transformation for a general polynomial here would be the 2 by 2 matrix defined by, okay. All right, and what we can notice here is that here, if we just go even think of this a bit further, the transformation on the basis vector. Now, I chose this particular example in a particular way. It doesn't necessarily always have to work out this way, right? Where here what we can see is that the dimensions here of P3 are the same as the dimensions of M22. So we map the basis vectors in the domain onto the basis vectors of the codomain, right? And now we could see here that by building this transformation, we made a deep connection between these two vector spaces, right? And in fact, we can work in between both of those vector spaces, right? And we can see that there's, in the terms of, how we deal with matrices and vector spaces, there's really not much of a difference there, right? There's an abstraction going on here that we could see that we can represent the polynomials as a 2 by 2 matrix. Okay? All right. So matrices and linear transformations on coordinate spaces like our Euclidean n spaces are interchangeable. And the last term that we covered says that a basis is all you need to define a transformation on any vector spaces. All right. Okay. Now the idea here is, how do I know that those transformations, or when are those transformations unique, right? And that's what we'll cover next.